So we want to talk quickly about sketching some polynomial functions, and this is an Engage New York activity that is from I distributed it in class, but I don't really think we talked about it too much. But it gives us a really strong idea of what a polynomial function is and what that looks like. So I want to take a quick look at these three pictures and their associated graphs. So any particular polynomial, when we look at this equation, we can identify a lot about the function. In particular, we can tell about the roots. And so if we think for each section here, x plus 1, well, what makes that 0? Well, I know for a fact that when x equals negative 1, there's a 0 there. And look at our graph. There is an x-intercept at negative 1, where the value of the function is 0. And again, if we look at the x minus 3 part, where is the x 0? Well, the x is 0, this thing is 0 when x is 3. And look at where the other function intersects the x-axis. And we could do that for all of these. So if I look at this second function, I see that I have roots at negative 3 because negative 3 plus 3 is 0. I have a root at 1 because 1 minus 1 is 0. And I have a root at 4 because 4 minus 4 is 0. And if I look at the graph, I can see, oh, there is an x-intercept at negative 3, there's an x-intercept at 1, and there's an x-intercept at 4. And we can count. So this is negative 1, negative 2, negative 3. Now these are really grainy looking graphs, but we could tell. And again, with this last one, here's the tricky one in this last particular equation, is that there's this x there. Well, what makes x 0? 0 makes x 0. Sorry, I meant to do 0 makes x 0. And because of that, we have this x-intercept right at 0. And again, at negative 4, so we have negative 4. At 2, so we have a root at 2. And at 5, so we have a root at 5, because all of those things make it 0. Well, what this activity is trying to get us to understand is that each of these types of graphs has a certain shape. Well, when I look inside of each function, I notice that I have x and x. So there are two x's. This function has a degree of 2. So the degree is an x squared graph. So it's going to have the shape of an x squared graph. If I look at this second graph here, I see x plus 3, x minus 1, and x minus 4. How many x's are there? Well, there's 3. So this is going to be a degree 3 polynomial. A third degree polynomial. And it's going to have the shape of an x to the power of 3 graph. And similarly on this last one, there's 1, 2, 3, 4 parts. So it is going to look similar to a fourth degree polynomial. So it's a degree 4 polynomial. And we know that because there are 4 potential roots, there are 4 x's, there are 4 potential roots. The most this function is going to have is 4. So in each of these graphs, we have exactly the same number as the degree. So if I'm looking at the number of roots, a degree 2 has 2 roots. A degree 3 has 3 roots. A degree 4 has up to 4 roots. Well, when we're talking about the number of relative maximum and minimum points shown in each graph, well, that's kind of an odd question. So if I think about this and I think that, hey, is it possible to have a degree 2 polynomial that has this quadratic shape to have 1 root? Well, yeah, if I shift this up just a little bit so that the vertex is just touching this x-axis, so if I move that up, then this polynomial has exactly 1 root. And if I move it even higher, it will have 0 roots. Now, if I do the same thing to this one, well, what does that look like? Well, I could move this point up so that it only touches once, and then I'd have 2 roots. So at most it has 3. It might have 2. If I move this vertex up so much that it's no longer intersecting this x-axis, then it has 0 roots there, but it will always pass at least once. So even though it might not be happening there will always be at least one x-intercept for a cubic function. See what you can think about, maybe pause the video and consider this, because it's an interesting question. We're going to move on real quick though. So now that we know different types of functions, we think about where are our zeros? Well, when I look in here, it looks like there's a 0 there because it crosses the x-axis there, and there's a 0 there. And to me, that looks like a root of 4 and a root of negative 1/2. Well, where do we see this 4 in the equation? Well, we see it right there because 4 is going to make that 0. So 4 minus 4 is 0. But where do we see this 1/2? And that, I think, is what's tricky. How does that give us 1/2? Well, what makes 2x plus 1 0? What will do that? And that takes a little bit of algebra, because we have to solve for the x. So I subtract 1 on both sides. It's fair because I'm subtracting the same amount on each side, and dividing by 2. So x equals, the 2's cancel out, x equals negative 1/2. And that's where I got that 1/2 from the equation. So by looking at the equation, we can tell immediately the roots. So we start getting into higher order polynomials. This one, as we look, has 3 x's, and let me just pause for a second because I want to show you that how many different, we're going to just set this to the side, we've got a bunch of different looking graphs, and I'm just going to kind of give you 6 or 7 examples of different types of functions that we know. Well, we know the x and x squared and x to the third, x to the fourth. And I'm going to show you what these look like. And this is x to the first, but it's just x. So we're familiar that if I just have an x, it's a straight line. X squared kind of has this parabolic shape. X to the power of 3 is introduced probably this year. It has this particular shape, and if I were you, I would pause the video when I'm done with these and write these down. But notice, take a look at where these all start, how many bumps they have. I notice this one starts up, and it has 3 bumps, and it's x to the fourth. The 5th one is going to start down. It's going to have 4 bumps and end up. The 6th is going to have 5 bumps and start up. X to the 7th is going to start down. So there's starting to emerge some patterns here. And I'm sure that you can notice lots and lots of patterns with these. But take a moment to consider those. Maybe pause the video real quick. Draw these out, because these 7 functions at least come up, and the pattern that you can recognize with these comes up quite a bit. But pause the video. I'm going to erase them in just a second so we can do the problem that was above. So as we sketch this graph, what am I thinking about? I'm thinking about what makes each one of these things 0. And I'm going to look at them piece by piece. Well, what makes the red x 0? Well, 0 is going to make it 0, so I know that there's a root at 0. What's going to make the blue piece 0? Well, negative 4 is going to make the blue piece 0. I just want you to pay attention and notice that these are 2, 4, 6, negative 2, negative 4, negative 6, negative 8. So when I graph negative 4, we go there. We can even go 2, 4, 6, 8, 10. And when I look at this green piece, I see... When I look at this green piece up here, I see, oh, 2 minus 2 is going to make that 0. So I got 2. So I graph a spot at 2. Well, this is a degree 3 polynomial. which I know is going to look like x to the power of 3. What does x to the power of 3 look like? It starts down, it goes through each root, and it kind of has just one big squiggle. So I'm going to mirror the x to the 3. Up, down, back up, and it goes through each of those roots exactly one time. Couple other examples here. We're going to refer back to those higher order polynomials. But when I look at this function, I see, oh, what makes this 0? Well, 0 makes that 0. And so I plot a point at 0. What's going to make this next thing 0? -3 is going to make it 0. So I plot a point at -3. And again, sorry, these are -2, -4, -6, -8. These go by 2's. When I graph x minus 2, what's going to make it 0? 2 is going to make it 0, so I plot another point at 2. What's going to make that 0? And I'm going to do that actually in green. What's going to make x minus 2 0? Well, it's going to be at the same point again, which makes this really interesting. When I see how many x's there are 1, 2, 3, 4 x's being multiplied together. So this is a 4th degree polynomial. This is a 4th degree polynomial. And it's going to have that sort of 4th degree shape to it. So it's going to kind of look like this, but notice that it's only going to cross the x-axis 1, 2, 3 times, which means this one got moved up. So let's take a look at what that looks like. If I'm graphing this polynomial, I start up, I go down through the root, comes back up through the other root. Instead of going back through, it's just going to touch and rebound. So right at this spot right here, notice it's not going through, it's just touching and going back up. That's because there's 2 roots at the same point. The root x is 2 and x is 2 here that make those pieces 0. So this is one of those special cases where if it doesn't go through, it's just going to rebound. All right, we just want to do a few more examples, so we're going to just make really bad sketches. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. These are really terrible sketches, and right now I'm not super concerned about the y-axis. So I'm thinking, what makes each of these 0? Well, -1 makes it 0. Plot a point at -1. -2 makes it 0. Plot a point at -2. And 2 makes it 0, so I'm going to plot a point at 2. This is a 3rd order polynomial because there are 3 x's, so I know it's going to have this sort of like just wicky-wacky shape. This starts from the bottom, goes up through the root, goes back down, comes back up. And they may look really bizarre. I mean, if we graph these in Desmos, you can see exactly what they look like. But you know that they go through the point -2, -1, and 2 because of the equation that we have up here. All right, 2 more examples. This is a really complex equation. Maybe I'll take a little bit more time on it. -1, -2, -3, -4, -1, -2, -3, -4. I'm just making really rough sketches. I mean, these are not perfect or close to being right in any way. 2, 3, 4, but they kind of help us understand the idea. So what makes it 0? 0. So I plot a point at 0. What makes it 0? -2 makes that piece 0, so I plot a point at -2. What makes this piece 0? Well, 1 makes it 0, so I plot a point at 1. What makes this piece 0? -1 is going to make that 0. I need to erase that, and -1 is going to make that 0. Gotta fix that. Did you see that? It's okay to mess up. 1 is going to make that 0 because 1 minus 1, there's where the 1 comes in. And then, surely last but not least, is going to be this 2, because 2 minus 2 is 0, so I plot a point at 2. When I go to graph it, I see there are 1, 2, 3, 4, 5. So this is a fifth. This is a fifth. degree polynomial. Fifth degree, so it's going to start down, kind of squiggle, have maybe a few squiggles in there. There's going to be 1, 2, 3, 4 bumps, I know for sure. So I'm going to start at the bottom. 1, 2, 3, 4 roots, fifth root, and done. Boom. So you can see kind of how this pattern emerges, that once I find what the zeros are, I can quickly determine the shape of the graph and what it's going to look like. Okay, we got 2 more slides real quick. Hopefully they'll go relatively quickly and you can pause and follow along before I do them and check your work as you go. This one is a little bit trickier because we've got one of those double roots right here. So there are really 1, 2, 3, 4 roots. So this is really a 4th degree, even though it doesn't quite look like a 4th degree, simply because we've got this double right there. So when I go to plot this, I know I've got -1, -2, -3, 1, 2, 3, -1. I'm going to label these -2, -3, 1, 2, 3. I've got a root at -1, and I've got a root at 3 for sure. But here I've got -1 for one of them, and +1 and +1 for the other. So I've got 1 is a +1, that's that one. And then I've got the other +1 also at the same spot. So it's going to have that 4th degree shape. Remember that 4th degree looking shape. But instead, at this spot, it's not going to go through, it's just going to touch. So we're going to go 1. Instead of going through, it's just going to touch. It's going to come back down and then go back through. And that spot is because of this power of 2 there. So it's that double root at that one spot. We've got one more just like this because I know that this double root thing is a little bit tricky, but I think that it ultimately is going to be beneficial for us to practice. Last one here. So again, I've got a double root at +1. So there's a +1, and then there's a +1 and a +1. Make my graph. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And I've got a positive root at 1. I've got a secondary root at 1. I've got a root at 3. I've got a root at -5. That's for one of the two. -5. And then I've got a secondary root at -5 as well. And when I count the number of x's, I'm even going to count the doubles. So there's 2 here, so 2, 3, and then there's another 2 here, 4, 5. So this is a 5th degree. And we've seen a 5th degree before in this video. It's going to sort of look like that, where it starts at the bottom, ends at the top, and instead of going through the point right here, it's going to touch, and instead of going through here, it's also just going to touch. So what does that look like? We start at the bottom, come up, it's just going to touch, come back down, it's going to come back up and just touch again, come back down and up through there. So in this case, and let's make that a little bit more through. In this case, there happens to only be 3 roots. We've got the first root, second root, and third root. Even though it's a 5th degree polynomial, this particular version only has 1, 2, 3 roots because it only touches the x-axis at this spot, and this spot. Even though it goes through that point twice, it's only 3 polynomials. So I hope this video was helpful in how to graph or sketch polynomial functions. It's very general shape of these things, but I think this is a valuable skill to kind of gain some intuition about what polynomials will look like. Thanks so much for watching this video.